titled Quantum Coherence Time as a Relational and Spectrally Constrained Property. It is actually a part of an ongoing work, and it's part of an attempt to model quantum coherence time. In fact, I submitted the paper under that category also, but somehow when it's scheduled, it came here. It's no problem. I am GregoryMathew from Department of Philosophy, Dharmaram Vidyakshetram, Bangalore. Here, it's a review-based paper, no experimental results or no computational conclusions, no such things are here. In fact, I am revisiting a few basics. So I request your patience. In order to begin my model, I have to revisit a few basics. There's two central aspects of my presentation is one, quantum coherence time is not solely a property of the qubit, but it is a relational one. Quantum coherence time is a relational one, and quantum coherence time is an operational window to quantum computation. These are the I'm not telling that it's a claim, but two insights which I want to substantiate during this presentation. These are this outline. Most of the things are basics only. Just to see the coherence time of a few quantum systems, qubit systems. See, there are qubit system with quantum coherence time hours, minutes, then seconds, milliseconds, hundreds, microseconds. We will take this slide once again during this discussion. And coherence time, quantum computing derives its computational power from quantum superposition and entanglement. Unlike classical bits, qubits must preserve their coherent quantum state long enough for computation. The practical measure of this ability is coherence time. Increasing the coherence time, enhancing the coherence time remains one of the central technological challenges in quantum computing. Traditionally, quantum coherence time is denoted by T2. It's a function of qubit properties. But experiments repeatedly show that identical qubits exhibit very different coherent times in different environments. Therefore, qubit alone cannot determine the quantum coherence time. Now we'll see another basic idea. It's decoherence. As you know, it is transfer of quantum information from the qubit into the environment. Qubit continuously interacts with the surrounding atoms, fluctuating electromagnetic field, thermal excitations, and thus decoherence occurs. So instead of existing in a coherent superposition, which is denoted by ket psi is equal to this equation, phase relation between the amplitudes is progressively lost, or the information is transferred to the environment. And decay, coherence time, such things can be represented as shown there. Now, the conventional methods to avoid coherence, there are conventionally several methods: ultra high vacuum, cryogenic cooling, electromagnetic shielding. There are many methods to reduce decoherence or to increase coherence time. But although these approaches have achieved remarkable progress, complete isolation is not possible. Or in fact, if a qubit is completely isolated, it will become a closed quantum system, and in nature, closed quantum systems in generally not available. So there is a trade-off between degree of isolation and availability for application. So there is a trade-off between the degree of isolation and availability for applications. Every physical qubit remains coupled to some environment. This naturally leads to another question. Instead of attempting complete isolation, can we engineer the interaction itself? Can the interaction itself be engineered? So can we somehow engineer or somehow adjust the interaction between the qubit and the environment? So there comes spectral engineering. Spectral engineering is actually actively modifying or manipulating the noise spectrum of a qubit's environment to protect its fragile quantum state. Decoherence becomes significant only when the environmental frequencies overlap the frequencies to which qubit is sensitive. This introduces a fundamentally relational viewpoint. The coherence time depends less on the absolute properties of the qubit and more on the spectral relationship between the qubit and its environment. Rather than interpreting coherence time as an intrinsic property of a quantum system, coherence time is treated as a relational property emerging from the spectral compatibility between the system and its environment. This spectral perspective naturally leads to a distinction between two fundamentally different paradigms for addressing decoherence. Now, one is here it is this decoherence and coherence. This is spectral match between the frequency spectrum of qubit and that of environment. When the spectral overlap happens, then decoherence is accelerated. Whereas if the frequencies are, if there is a spectral mismatch or the frequencies are entirely different, then coherence is promoted. I'm not going to the technical details of such things. Now, spectral overlap leads to two fundamentally different paradigms, namely decoherence control versus elimination. Decoherence control means in this approach, environmental spectrum remains unchanged, but dynamical techniques are employed to reduce the effective coupling between the system and its environment. Examples include dynamical coupling sequences, error correcting encodings. So all these methods can significantly extend coherence times, but do not fundamentally alter the spectral structure responsible for decoherence. Whereas in the case of decoherence elimination, it occurs when the environmental spectral density itself forbids information transfer between the system and the environment at low frequencies. In this case, the Hamiltonian structure of the system-environment interaction intrinsically suppresses decoherence channel. The resulting bounds on decoherence arise not from active control but from the spectral properties of the environment itself. Here, ohmic relations are also relevant. Ohmic relations are shown here. To formalize the above mentioned distinctions, we analyze the pure dephasing dynamics of a qubit coupled to a bosonic environment using a general spectral density formulation derived from the spin boson Hamiltonian. If the environmental spectral density behaves at low frequencies as j omega proportional to omega raised to s, where j omega is the spectral density and omega is the frequency. Here two cases, in fact there are three cases, s less than 1, s equal to 1, s greater than 1. So in the case where s, the exponent less than or equal to 1, it is corresponding to complete decoherence, whereas s greater than 1, that is called a super-ohmic case. In that case, coherence is promoted or decoherence is blocked. This is a plot for the ohmic. This is ohmic, this is subohmic and supraohmic cases. In these cases, if the frequency of the qubit falls in the low frequency region, then in the case of supraohmic, in the case of this supraohmic behavior, there will be spectral mismatch and coherence time will be enhanced. Whereas in the other two cases, there will be overlap between the qubit frequency and the environmental frequency. There will be overlap between the qubit frequency and the environmental frequency spectrum, and decoherence occurs. Spectral mismatch, again, I've shown a graph. Spectral mismatch where this qubit frequency and environmental frequency, when they match, strong decoherence. If they are not equal, if they mismatch, weaker interaction, in that case, coherence time increases. So spectral overlap, which is a decisive parameter of quantum coherence time, that is given by this mathematical expression, or you can say coherence is determined by the degree of spectral overlap. This is the essential technological meaning of the relational perspective. And this is another version of the spectral mismatch. This is the qubit frequency. This is corresponding to the environmental frequency. In fact, this is for a specific qubit system in which an electron is placed on a helium bath. So this is this shows spectral mismatch in the case of qubit system with electron on a helium bath. See here, the environmental frequencies are in fact corresponding to ripon and other quasi-static charge fluctuations, but that is much different from the qubit transition frequency. So decoherence is not much happening there. Fourier transform can be used to, it is from the time domain to frequency conversion. For such a mathematical theoretical work, Fourier transform is used. Now, this is the experimental setup of a particular qubit system. Electron placed on a helium bath. I'm not going to the technical details of these things. There are so many qubit systems, as I shown in the beginning of the talk, with the reported quantum coherence time very encourageable or technically relevant values. Now, why liquid helium? Liquid helium has this kind of characteristics: extremely low noise environment, and no nuclear spin, high electron mobility, weak spin orbit coupling. So these characteristics in fact promote it as a good candidate for a quantum computer. Now electrons on the surface of superfluid helium interact primarily with the ripons, which are ripons means quantized surface excitations on helium interface. The coupling between electrons and ripons yield a strongly supraohmic spectral density, thereby significantly suppressing low frequency decoherence channels. As a result, decoherence function converges and system can exhibit long time coherence saturation rather than complete decay. This intrinsic spectral suppression suggests that electrons on the superfluid helium may offer a platform where decoherence is not merely controllable but structurally limited. Here in this case, in the case of helium bath electron based qubit, it is not controlled, but coherence is structurally limited, not simply controlled. So electrons flowing above liquid helium provide one of the cleanest non-solid state quantum system. Several unique properties of this liquid helium contribute exceptionally for long coherence time. An isolated electron above liquid helium is governed approximately by Schrodinger equation, which is IH cross del psi by del T equal to H psi. The Hamiltonian contains kinetic energy, image potential, external electric field, and weak coupling to surface excitations, or which may be called ripons. Because the surrounding environment is exceptionally quiet, decoherence occurs much more slowly than in many semiconductor platforms. Theoretical work predicts the quantum coherence time of electrons on liquid helium around 10 to 100 milliseconds. So under realistic conditions, with some proposals suggesting even longer coherence time if the noise can be strongly suppressed, achieving such values experimentally remain as an active area of research. Now, in the case of In the case of this qubit based on electron, okay, qubit based on electron versus ensemble, it is found that single electron qubit carrier coherence time is larger than that of ensemble. In the case of ensemble, additional interactions accelerate decoherence. That is the reason. And in the case of this, it is found that these are the same electron on helium bath, but the configuration of the electrodes, this configuration of the electrodes in fact vary the quantum coherence time. So quantum coherence time depends on that experimental, even the experimental setup also. When there are many electrons, quantum coherence time decreases than that of the single electron, and with this configuration it is further increasing. So quantum coherence time is again relational in the sense, see, it's a function of qubit environment, spectral overlap, and many other technical parameters related to the configuration of the setup. Now, this is another, sorry, oh my god, this is another table which is showing the quantum coherence time, corresponding environment, and some remarks. This is what I referred in this presentation, electrons on liquid helium. Though it is only millisecond, due to certain technical parameters, technical qualities, it is considered very, very promising. Okay. Now let me. Now a question remains: does a quantum computer need very large coherence time? In fact, no, not necessary. It need not have hours of days of quantum coherence time. The important parameter is not quantum coherence time as such, but the but the ratio coherence time by time for a gate. The 100 microsecond is the coherence time, 20 nanosecond is if it is a gate time. Then with that kind of a qubit, only 5000 gate operations are possible. So your algorithm and the number of gates, that's a parameter, not quantum coherence time as such. Coherence time by gate time, that is the decisive parameter there. The ratio is more meaningful than the coherence time. Now, if someone builds an extremely long coherence qubit, will it lose coherence during storage? Of course, during classical storage, quantum coherence will be lost. But quantum storage means if you want to preserve that quantum stage for a longer duration, then you need a high coherence time. Let me conclude. So, quantum coherence time is a dynamic relationship. It is not a static object. The relational picture, coherence is not a container that holds information, but it is a condition that permits relational evolution. Coherence time is not simply intrinsic, it can be engineered. Then it's a computational window. It's not just lifetime of a qubit, but it's a computational window. It's an operational window which help you to explore more to the nuances of quantum computation and quantum phenomena. Thank you.
Dr. Mathew, since we are running against time, we can have one quick question.
Sir, I have time up to 4 o'clock. So 7 minutes remain. No problem. Okay. No.
There's I've been told by organizer that's
Okay.
Is there any question? If not, then we can thank Professor.
Thank you.
Thank you very much for finishing in time.